Double-acting propellers do not have springs or gas pressure to assist in changing propeller pitch. Thus, all of the actuation, both to fine and coarse pitch, must be hydraulic. Engine or reduction gearbox oil is once again used as the hydraulic medium for this purpose. The inset diagram of a dry sump oil tank, which you may remember was used previously in the lesson on engine lubrication, illustrates how a protected source of feathering oil is provided. The oil pressure required for feathering the propeller is generated by an electrically driven pump, which may be activated by a feathering button in the cockpit. With the exception of operating the feathering pump, the basic control selection for feathering the propeller remains the same. That is, selection of the propeller control or condition lever, operation of a separate feathering lever, or, on some turboprop systems, moving the HP fuel cock to the feather position. For the purposes of this lesson, we'll consider that we are feathering a propeller which has twin lever control. The propeller control lever is brought back through the fully coarse position to the feather position. Alternatively, where fitted, the propeller feathering lever is operated. This action lifts the landed valve in the propeller control unit upwards, thereby connecting the feathering pump oil line to the coarse pitch side of the pitch change piston, and allowing oil to drain from the fine pitch side of the pitch change piston. The feathering button in the cockpit is pushed in, energizing the feathering pump solenoid relay to supply the feathering pump. It also energizes the holding coil, which keeps the feathering button depressed for the time being. Feathering oil now passes through the ports of the landed valve, pushing the pitch change piston so that it moves into contact with the feathering stop. Oil pressure will now build up within the system, eventually operating a pressure-operated cutout switch, which will interrupt the supply to the feathering button hold-in coil. This causes the feathering button to release, which terminates the supply to the feathering pump solenoid relay, which in turn breaks the supply to the feathering pump. If the propeller is allowed to windmill, the forces generated will cause it to try to unfeather itself. Moving the propeller blades a few degrees below the feathered position will cause the propeller to rotate, and centrifugal turning moments will tend to move the blades towards a finer pitch. This will cause the propeller to rotate faster, until it comes under the control of the propeller control unit. The propeller control lever of the unit being unfeathered should be placed in line with that of the operating engine or engines, and, where fitted, the feathering lever should be reset. This allows the speeder spring to push the landed valve down. It also helps to minimize the yaw which will inevitably accompany the effect of unfeathering. Pressure oil can now be directed to one side of the pitch change mechanism to move the piston towards a finer pitch, and coarse pitch oil will be allowed to drain from the other side as it does so. The feathering button should now be pressed. This starts the feathering pump running, which will supply the pressure oil to the pitch change mechanism to move the blades away from the feathered position towards fine. Once the propeller starts windmilling, the feathering button should be pulled out. Pulling out the feathering button overcomes the holding coil. When the contacts of the feathering button are opened, they break the supply to the solenoid relay, the contacts of which are supplying the feathering pump. Thus the feathering pump stops. The rest of the restart drill is accomplished in accordance with the aircraft operating manual. To reduce the workload on the pilot in the event of an engine failure, some propellers are equipped with an auto-feather system. The system is normally active during takeoff and cruise conditions only. For example, on a turbojet engine, with the high-pressure fuel cock open and the power lever set to high power, a signal of low torque from the engine torque meter system will automatically feather the propeller. Should either of these conditions not be met, the auto-feather system will be rendered inactive. This diagram shows an auto-feather system installed on a typical double-acting propeller arrangement for a turboprop engine. It consists of an additional oil pressure line supplied from an electrically operated feathering pump to the underside of a valve lift piston in the feathering mechanism. Control over this oil pressure is provided by an electrically operated solenoid valve. In the event of an engine failure, and provided the engine controls are set to the high power configuration, a low torque signal will complete the auto feather circuit and energize the valve lift solenoid and feathering pump. This delivers an independent supply of feathering oil to the valve lift piston, which raises the landed valve to the coarse pitch position. The high-pressure oil supplied by the feathering pump is now fed to the coarse pitch side of the pitch change piston, pushing it onto the feathering stop. As the piston moves, it displaces the fine pitch oil to return. The feathering stop is fitted within the pitch change mechanism, the position of which allows the propeller blades to take up a position edge-on to the aircraft's airflow, where they will generate zero aerodynamic force in either direction. The propeller should not now windmill. The propeller control unit incorporates a flight fine pitch stop solenoid, which controls a supply of high-pressure oil to a flight fine pitch stop mechanism in the propeller pitch change cylinder. When the solenoid is energized, oil pressure is directed to withdraw the flight fine pitch stop, thereby allowing the pitch change piston to move below the flight fine position and into the beta range. When the solenoid is de-energized, oil pressure is removed, and the flight fine pitch stop is engaged by spring pressure. Use your mouse to press the repeat button, which will enable you to see the removal of the flight fine pitch stop again. Most turboprop engines are provided with a system of propeller control which is defined by alpha and beta ranges. The alpha range is used at high speed, during the takeoff run, in flight and during the initial high-speed part of the landing rollout. The alpha range is selected by moving the engine power lever to a position at or above flight idle. The beta range is used on the ground only. It's selected during the landing roll by first removing the flight fine pitch stop, or FFPS, which was previously engaged to prevent the blades moving to ground fine pitch in flight, and then moving the engine power lever to a position below the flight idle position. On systems not equipped with a hydraulic flight fine pitch stop, the power lever is moved through a flight idle detent or gate. With the propeller blades functioning within the alpha range, their pitch is controlled automatically by the propeller control unit, whilst within the beta range their pitch is controlled by the operator's movement of the engine power lever. In most aircraft, the selection of the beta range is made by movement of the flight fine pitch stop, the FFPS lever. Alternatively, in some systems the selection can be made via the condition lever, that is the RPM lever, itself. A warning light, usually blue or amber, illuminates whenever the flight fine pitch stop is disengaged. Additionally, other warning lights may be provided, which illuminate whenever the propeller blades are moved below the flight fine pitch position, that is, into the beta range. While the aircraft is taxiing, there is insufficient RPM available to bring the propeller control unit on speed, and it's therefore unable to take control. Propeller RPM is controlled by movement of the engine power lever within its range below flight idle. As power is applied for takeoff, the flight fine pitch stop lever is forced into the flight position by the action of moving the power levers to the takeoff power position. The FFPS light and or beta lights are extinguished. As the pitch of the blades coarsens to allow the propeller to absorb the increased torque being produced by the engine, the piston in the pitch change mechanism moves into the flight pitch range or alpha range. This allows the flight fine pitch stop to engage under spring pressure, thereby preventing the piston from moving below the flight fine pitch position. There is now sufficient RPM available to bring the propeller control unit on speed and into a controlling condition. Many turboprop aircraft and a few high-powered piston-engined aircraft are provided with a means to allow the operator to select a superfine pitch, or to aerodynamically reverse the pitch of their propellers, or even in some cases to do both. In the case of a superfine pitch selection, a fixed abutment stop in the pitch change cylinder allows the piston to take up a position at or near 0 degrees. This is known as a disking position, and is used for starting and initial acceleration of the engine, and for aerodynamic braking during the landing roll. Superfine pitch is commonly called ground fine pitch, and its position is several degrees finer than the finest pitch available in flight, which is called flight fine pitch. The propellers of more modern aircraft may have a much greater range of blade movement in the beta range. The range can extend from around plus 8 degrees to minus 30 degrees pitch, which is full reverse. The beta range of this type of propeller is selected in a similar manner, and at the same point in the landing run as the previously discussed system, that is, during the high-speed initial part of the landing rollout. In this case, however, the braking effect obtained from the selection of reverse pitch is much more effective than that which would result from merely the selection of ground fine pitch. With the propeller in reverse pitch, the forces on the propeller blade are as shown here in the small diagram on the right of the screen. As you can see, in reverse pitch, the forces generated by the propeller will produce a braking effect to actively decelerate the aircraft after landing. On landing, the flight fine pitch stop lever must be moved to the disengaged or ground position before the engine power lever can be moved below flight idle. On systems not equipped with the removable flight fine pitch stop, the power lever must be moved through a fixed gate or detent. On some aircraft, microswitches, which sense that the weight of the aircraft is on the wheels, ensure that this selection cannot be made in the air. Once the power levers are moved below flight idle, the propeller blades move into the ground fine pitch range, and the propeller control unit relinquishes control. Propeller RPM is now controlled by power lever movement. The forward velocity of the initial landing roll, combined with low RPM and low blade angle, produces a zero or negative angle of attack. This reverses the total reaction produced by the propeller, which acts to slow the aircraft in its landing roll. This condition is known as disking braking. Propellers which can have their pitch angle made even more negative are known as fully reversing propellers. As the power lever is moved further rearwards into the reverse pitch range, the blades move into the negative pitch position. The reversed total reaction produced now increases. This exerts increased load on the engine, so engine power is increased in order to maintain a constant RPM. The engine power and reverse airflow through the propeller is now being used to slow the aircraft down. This condition is known as power-on braking. Many multi-engined aircraft are provided with a visual indicator, which is called a synchroscope, which indicates the RPM differences between the slave engines and the master. As you can see from this picture, the presentation consists of miniature propellers, which rotate to show when an RPM difference exists, and whether the slave is faster or slower than the master. In order to reduce the amount of vibration which can damage aircraft components, and also to reduce noise harmonics which can occur on propeller-driven aircraft, the engine propeller assemblies are often provided with a means of making the RPM of each unit the same as all the others. A synchronization system will reduce the annoying harmonics which can be produced by out-of-sync propellers, and also lower noise levels significantly. Electromagnets in the head of the rotating assemblies of the propeller control units of each engine are used to generate an RPM signal. An aircraft fitted with such a synchronization system will have a designated master engine, and other engines will be specified as slave engines. The signals from the propeller control unit of the master engine and those from the slave engines are sent to a control unit where they are compared. With the synchronizing system engaged, Any RPM differences between the master and slave engines will be sensed in the control unit. The control unit generates proportional, positive or negative current outputs which are sent to torque motors. The torque motors are mounted on the slave engine propeller control units in such a way that a signal indicating that the slave engine is running at a lower RPM than the master will cause the slave engine's torque motor to turn in order to fire off its propeller, thus increasing its RPM until no discrepancy exists between the slave and master engine speeds. If, on the other hand, the control unit receives a signal indicating that a slave engine is running faster than the master engine, then it will send a signal to the appropriate torque motor to coarsen off the propeller blades of that slave engine to reduce its RPM, until once again no discrepancy exists between the slave and master engine speeds. So, the torque motor rotation resets the speeder spring on the affected slave engine's propeller control unit, which will ensure that it is once again synchronized with that of the master engine. When no difference in RPM exists between the master and the slave propeller, no output is sent to the slave torque motors.